All right, so Assalamu alaikum. So today, lecture 15, we're going to give a concrete example of phonons in 2 dimensions. So we have a 2-dimensional crystalline structure, exists in 2D only. For example, many such examples exist, such as graphene, the most pronounced of an example of this kind. So let's look at an explicit calculation on how the dispersion relationship for phonons can be calculated in such a 2D material. So welcome to phonons in 2D. So the model that we have is that a 2-dimensional structure exists, and we suppose that it's a square lattice. And there are phonons existing inside this 2-dimensional lattice. Phonons, as you know, are oscillations inside the collective oscillations inside the crystal. And we can model this solid as a grid of points arranged on a square framework in which neighboring atoms are connected by these spring-like structures. So the model that we have for the interaction between 2 neighboring spins is of a mass attached to a spring with a particular spring constant, as you all know. And we suppose that the interaction between an atom and its neighbor is defined by this spring constant alpha, which is a force per unit length, and each of these atoms is of course connected in a pairwise fashion to its nearest neighbor. But we also assume, to add a little bit more spice into this example, that in addition to these nearest neighbor interactions, we also have an atom connected to the next to the nearest neighbor atom through another interaction whose strength is given by beta, again in a spring-like fashion. So if you focus your attention on this atom, let's call it atom number 0, it's connected to 1, 2, 3, 4. This is atom 0 connected to 1, 2, 3, 4. These are the nearest neighbor interactions, but the atom is also connected to the next nearest neighbor atom, 5, 6, 7 and 8, through these spring-like bonds, and it's expected that this bond strength is beta, which is expected to be slightly softer than alpha. So this is the model that we're going to work with. Now in our previous lectures we've already looked at equations of motion. So we do know that if all of these atoms have an identical mass m and the displacement of each atom from its equilibrium position is s, nth atom, 8th atom inside the basis along a direction I, the double derivative of this displacement needs to be equal to a force. And we've seen that this force, the negative of this force, so this equals a force, I take the force to the other side. So the negative of that force is simply phi NAI MBJ SMBJ summed over M summed over BJ. So this is our equation of motion. So what we have here is that each atom which is indexed by its reciprocal lattice position n, by which atom it is inside the basis A, B, C, and by the direction I, J, K, could be X, Y, Z, is equal to a force, and that force is coming out because from all other atoms which are displaced. So all other atoms which are indexed by labels M, B and J, M is some lattice point, B is again the atom inside the basis hooked onto that lattice point, and J is the direction. All right, and you multiply this with the particular constant, and then you sum up over all other atoms M, B's and J's. So this is our equation of motion, and we've also seen that this term can also be lumped together if I assume an ansatz S NAI equals some 1 over under root m, some amplitude u ai, where the index n is suppressed. I've already explained this, and a wave function and an exponential factor e raised per I k r n e minus I omega t. If we insert this ansatz into this equation of motion, we get an alternative form for the equation of motion, which is given by m u a I, sorry, minus omega square u a I plus d a I b j u b j summed over all b j's equals 0. Okay, where this is a matrix element in the dynamical matrix d a I b j, and is given by the sum over all of these spring constants phi n a I m b j e raised per I k dotted with r m minus r n. If all the atoms are identical, this term is simply m in the denominator. If they're not identical, you need to multiply ma with mb and take the square root, and you sum up over all m's. So these are three alternative ways of writing the equation of motion. We start off from here. Number one, this is after lumping together these force constants into the dynamical matrix element, and the dynamical matrix elements are defined in this fashion. Okay, so this is where we all started off from, and one of the homework problems also asks you to kind of employ these derivations. So now in our example here, in this two-dimensional structure, how many atoms do we have in a basis? So we are assuming a monoatomic system, so there is just one atom inside the basis. So there is no B, there is just one A. A is 1. So we don't need to write that A, in fact. And there are two directions, X and Y. So if we use these prescriptions to write down the equation of motion for our system and find out the elements of the dynamic matrix, this is how we will proceed. for our case, we have I and j are just x and y. Each of I and j can just be x and y, and there is only one A. There is no B. Just A is just one. So I can omit this variable A. So our equation of motion is minus, there are two equations of motion because it's a two-dimensional problem, minus omega square u along x. So now I'm going to use equation number 2. Minus omega square ux plus d x x ux plus d x y uy equals 0. So this is equation number 3a, okay, which is simply coming out from equation number 2 when my I is x, okay, and my j varies from x to y. So this is equation number 3a. Likewise, equation number 3b will become minus omega square uy plus dy x ux plus dy y uy equals 0. This is equation number 3b. Here I equals y. So these are the two equations that we wish to solve, and we also wish to find out what these d's are. These d's are the elements of the dynamical matrix. So D is a matrix whose elements are dxx, dxy, dyx and dyy, and these elements are given by equation number 3. And do keep in mind that when we compute this sum over m, the result is dependent upon A, I, B and J. So it depends upon which basis element you're talking about and which directions you're considering. It does not depend upon m because you're summing over m's. And it does not depend upon n because of the translational invariance. So you go to any point on the lattice, you go to any n, this matrix element shouldn't change. So it's independent of n. Okay? In fact, if you look at this element here, phi, for 1D, we've already defined what phi looks like. In 1D, we do know that this phi NAI MBJ in 1D is simply the double derivative of the potential energy with respect to the positional variables computed at the equilibrium point. Right? So this is how we've defined phi in 1D. And this is a force constant. Energy, the gradient of energy is a force, and you take gradient once again, it's a force constant. So this is how phi was defined in 1D. Now we have a two-dimensional problem, so the situation gets slightly more complex. So let's find out what corresponds to phi. What is the force per unit length on an atom that is constrained to move not in 1D but in 2 dimensions? Okay, yes.
MBJ.
MBJ. This is MBJ. MBJ. All right. So do remember that if you look at this term here, this phi, what does physically represent? This is a force. This is a force on the nth atom. the 8th atom inside the base is on the nth location in the I direction, right? All of this is a force on the 8th atom in the along the ith direction. Now this force, so consider here, so suppose considering the force applied on this atom in a particular direction, and all the neighboring atoms with which this atom is interacting, they can move in either direction. They can move along x, they can move along y. So if I displace this atom along x, I will get a component of the force on this atom along x. I can also get some force on this atom along y, even though I moved this atom along x. So for each of the directions in which a neighboring interacting atom moves, x or y, I can get a force on this atom along x or y. So that's why this term is really representing a force on the Na atom along the I direction posed by an atom Mb which has displaced along the j direction. Correct? This is what this physically corresponds to.
वो हम इसको half kx से सकते हैं.
So it's proportional to this is related to k. Okay, but in 1D everything is clear. That's why you were able to use this definition. Okay. Now in 2D we would like to find the analogous formula for computing the phi's. Now suppose I have two atoms. This is atom number on location n. This is atom on location m. These are two lattice points. And since it's monatomic, I don't need to consider A or B. Alright, so now these points are connected by a vector. So that vector, if this position vector is Rn, this position vector is Rm, then this vector joining m to n is Rm minus Rn. Let's call this W. Now what we would like to do is we would like to displace atom M along some arbitrary direction. Let this displacement be S, M, Sm, vector Sm. Okay, so this is along some direction. Now if this vector M is displaced and the displacement is Sm, Sms are all the displacements from equilibrium, a force acts on this atom. Now a force acts on this atom in a direction in which the energy change is maximal. So it's a central force, it's a mechanical force, it's a central field that is interacting atom N with M, it's a central field. It only depends upon the distance between two atoms. That's our assumption. So this means that the maximum energy change is when we move along the interatomic vector, right? So the direction of the force that acts on N is along this interatomic vector. So the force on atom N, which is a vector, is going to have some strength. That strength is given, suppose this interaction strength is alpha, this is the spring constant, force per unit length, alpha. And the displacement is S M. and the direction is q, unit vector w, sorry, because it's along the interatomic, right? So this is the amount of the displacement of the atom m, which is in some arbitrary direction, okay, and this is the direction of the unit vector, the direction of the force.
It's a dot product of R M and Rn.
Just a minute. N imposed by a motion displacement of the atom m, okay. Now let's take this idea a bit forward. Suppose the atom m moves along the j direction, right, some j direction, right. Suppose this is my j direction arbitrarily, this is a j direction and there is an I direction, okay. So if the atom moves along the j direction, I want to compute the force on atom n when this neighboring atom has moved along the j direction, okay. So then this kind of prescription is going to change a little bit. F on atom n, when the atom m has moved along j direction, this force is still alpha, it's still along w unit vector, but now I would like, the magnitude is still Sm. However, now I would like to take the component of the vector Sm along the j axis. So what is that component? That component is given by the projection. This is given by Sm along the j direction, correct? So now instead of Sm, I have a component of Sm. But Sm component along the j direction is given by, it's given by S M W dotted with J. SMJ, right? So this remains preserved. So what I would like to do, I would like to, this SMJ is the component along the j direction. So I need to take the dot product of the internuclear vector with j. Now I would like to find the component of this force along the I direction.
सर वो बस ऐसा नहीं होगा जब आपने वो डॉट प्रोडक्ट ला दिया?
एक मिनट. The nth atom moves along some direction. However, we assume that there is no shear, which means that we only need to take the component of m along the internuclear vector. So if Sm is moving in an arbitrary direction, what really matters is the component of Sm along the internuclear vector. So this is Sm vector dotted with W unit vector to begin with. All right, so the force on this atom is along the internuclear vector. That's why we have this unit vector W. And what really matters is the component of the displacement which is parallel to the internuclear vector. Because the component of the displacement that is perpendicular to the internuclear vector is causing shear, which is not allowed inside this spring model. So we start off from here. So this is Sm dotted with W. This is what we start off with. Now what we would like to do is we want to have the jth component of this vector. Okay? So when we have the displacement S explicitly along J, we need the jth component of this vector. The jth component of this vector is simply, now what is this? The magnitude of this. The magnitude of this is Sm along W, but now we would like to take the projection along the J axis, so this becomes Smj, and the directionality is represented by omega dot product with J, and then this we have this additional W. Okay, finally we would like to find the component of this force along the I direction. So now I remove this vectorial sign. This component is all of this is a vector. This is a magnitude, 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 and this is a vector. So I need to take the projection of this entire vector along I. So I will be left with alpha Smj W unit vector I. So this really is, in my two-dimensional problem, my phi NAI MBJ. All right, Sarim, ठीक है? Now in our two-dimensional problem, we need to calculate the D's, right? We need the dynamical matrix. For the dynamical matrix, we need to calculate the phi's. So let's now try to find out all the phi's. In fact, we would just like to write down the equation of motion. So let's write down the equation of motion along an X for some atom. And we focus our attention on atom number 0. All right. So along X, we have minus omega square Ux. Now I'm going to write down equation number 3a plus, I need dxx. Now dxx is given by equation number 3. I need to put in I equals x, j equals x in equation number 3. So I will get 1 over m phi. Now I'm talking about atom number 0 here. So phi 0 x. And in the superscript, I need to iterate over all possible m's, right? All possible m's with which this atom at location 0 is interacting. And all those m's are 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so I need 0x, 0 itself x, because if an atom moves on its own, it will interact with itself as well. It will cause some force on itself because of that's called the restoring force. Plus, now I need an exponential factor. The exponential factor comes from Rn minus Rm minus Rn. So it's really the difference in the position vectors between these two atoms, 0 and 0. So this difference is 0. Plus phi 0x 1x with an e raised power I. Now I need to find, so k dotted with the internuclear vector that connects atom 0 and 1, which is this vector, right? Let's call this vector W1. So now I'm going to, for convenience, this vector is W1, this vector is W2, this is W3, this is W4, right? Let's call this vector W5, this vector W6, this vector W7, and this vector W8. So I have these 8 vectors. So I get EIK dotted with W1 plus phi 0x, and let's first do, instead of 2 let me put 3 here, 0 3x E IK W3, but W3 is minus W1, so I just put minus IK W3.
W1.
So this is the difference, or W1. 0 and 3, W3, which is minus W1, plus phi 0x 2x EIK W2 plus phi 0x, and then I have 4 comma x E minus IK W2. So I've taken into account all interactions between nearest neighbor atoms. Now I need to take into account the interactions between next to nearest neighbor interactions. So plus phi 0x 5x EIK omega 5 plus phi 0x 7x E minus IK omega 5 plus phi 0x 6 comma x E IK omega W6 plus phi 0x 8x E minus IK W6. This must equal 0. And this, oh sorry, this is not as complete as yet. This is ux. This multiplies with ux. Still not complete, finished. We're not finished as yet, because we must take into account this term as well. So let's patiently write down the other terms. It's just a long calculation, but very systematic. 1 over m phi 0x 0y plus phi 0 x 1y E I K W1 plus phi 0x 3y E minus ik W1 plus phi 0x 2y E plus ik W2 plus phi 0x 4y E minus ik W2, and now the next to the nearest neighbor interactions, plus phi 0x 5y eik W5 plus phi 0x 7y e minus ik W5 plus phi 0x 6y e plus ik W6 plus phi 0x 8y e minus ik W6 uy equals 0. So I get the first top row inside the dynamical matrix. Now I need to compute these phi's, and those phi's are computed by the equation that I've written for the force over here. So if I compare equation number 4 with equation number 1. So I compare equation number 4 and equation number 1. This term here is the corresponding phi, what I've written in blue. Equation number 4 compared with equation number 1, the term that I've written in blue, which is some force constant alpha or beta, W unit vector along I, W unit vector along J. This thing is the alpha, this thing is the phi ij, correct? Nibj. For 1D, there is only one I, which is along x, say. So this term turns out to be 1. So you just left with alpha or beta. But for 2D, you need to consider these directionality factors as well. So now, using this equation number 4 and equation number 1 and this definition for the phi's, we can calculate all of these phi's. Okay, for example, phi 0x 1x. This is now this is our phi. This is 0x 1x. The strength is alpha, and I need W1 dotted with unit vector x, W1 dotted with unit vector x, because there's x's on both sides and the vector that connects 0 to 1 is W1. Now the unit vector W1 is along x itself. So unit vector x with itself dot product is 1. This gives me alpha. Right? Likewise, phi 0x and 1 or 3x is also the same. What about phi 0x and 2x? So of course 0x and 1x and 0x and 3x are both of them going to give me alpha, correct? Because for 3 this becomes W3, which is minus W1, W3 minus W1, but it's along x, so these two negatives cancel, I still get alpha. But what about 0x and 2x? 0x and 2x is alpha omega 2 dotted with x, omega 2 dotted with x. Now omega 2 is along y direction. So this term along with 0x, 4x is 0, right? So these terms are 0, whereas these terms are alpha. Correct? Let me check this.
Implicit diagonal by entries का तो फर्क होगा.
By the way, one thing I would like to mention is equation number 1, the left hand side is the negative of the force, isn't it? That's the equation of motion. So this is really negative sign here, okay? So this term is minus alpha. Okay, so you can see it's the negative of the force because you would simply know that mx double dot is equal to some force. So mx double dot minus f equals 0 is the equation of motion. Okay, so now we've computed these phi's. So which phi's have we computed? We've computed this phi, we've computed this, and this one. Now let's compute the phi's corresponding to the next to the nearest neighbor interactions. So phi 0x and 5x. Now the strength is beta, so put a minus sign, minus beta, W5 x, W5 x. All right. Remember, these are unit vectors that we're talking about. Now W5 is, the vector W5 is AX plus AY, isn't it? Because if this length is A, the lattice spacing A, this length is A. So this vector is AX plus AY. X and Y are unit vectors. So I take the magnitude of W5 is A square plus A square square root. It's under root 2A. Okay. So this term here becomes minus beta. The dot product of W5 with X is A. This is A as well, so A square divided by 2A square, which is the square of this. This becomes 2, minus beta over 2. Likewise, if I calculate phi 0x and 7x, this will also yield minus beta over 2. In fact, if I were to calculate this for any 0x, 6x, 0x, 8x, it's going to be minus beta over 2. We can check this. Let's check this for, say, 6x. For 6x, minus beta omega 6 w6x w6x. Now w6 is which vector? Is minus ax plus bx. So this will give me minus a turn out to be positive. So I will still get a minus sign, minus beta over 2. All right. So I have computed all of these phi's. This phi, this phi, this phi, this phi, with one exception, with the self phi. That I haven't computed as yet. That I'll do in a minute at the end. Okay. So now I need to compute these cross phi's. Right. So if I look at 0x and 1y, so these are the nearest neighbor interactions and they're along x and y. The interatomic vectors are along x and y. But I need the projections along x and y. So if I were to take W1, say, and once I take the projection along x, I get non-zero, but I need a projection along y, I'll get 0. So all of these terms, in fact, these terms will yield 0. There will be 0, correct? So all the phi 0x, any ky is 0 where k is 1, 2, 3, 4. However, this might not be true, this will not be true for these phi's because the interatomic vectors are now diagonal. So let's compute 0x 5y for example. So phi 0x 5y. What's the strength beta? With a minus sign, minus beta, I have W5. Once I take the dot product with x and once I take the dot product with y. Now W5 itself is given over here, right? This is my W5. So this yields minus beta a square over 2a square minus beta over 2. Right, so let's check phi 0x 6y. This is minus b w6 x w6 y. This gives me minus beta. Now notice that w6x is minus a. This term is plus a. And I need to divide by 2a square. This will give me plus beta over 2. This will also be the case for phi 0x and 8x, whereas minus beta over 2 exists for phi 0x 5y and phi 0x and 7y. Okay. Now what I would like to do, I would like to compute the two self terms. First of all, let's see what does this term mean, phi 0x 0x. Now let me draw my network of atoms once again. So this is my network of atoms. This is atom number 0. Now this term really means what is the force on atom number 0 along the x direction when this atom itself has moved in the x direction. Correct? Now this force would simply be the force that acts on this atom if this were to remain stationary and all the other atoms would move in the opposite direction. All the other atoms. 1, 2, 3, 4, 5, 6, 7 and 8. So if this atom moved, say for example, plus S0 along the x direction, then this force would be the same as if all the other atoms, negative of the force, this would be the same as if all the other atoms would move in a negative S0x direction. Correct? So this phi 0x is the same as the sum over all phi 0x any let's say tx, where t is 1 to 8, right? Minus sign. Okay, so now I've already calculated all of these terms, 0x, and so these are minus alphas, and there are 2 of these terms, and there are 4 of these terms, right? So there are 2 terms with alpha and there are 4 terms with beta over 2. So the sum of all of these terms will be 2 alpha plus 2 beta with minus sign. So this will give me 2 times alpha plus beta. Now a similar argument can be shown for 0x and 0y.
पहले 4 तो वैसे ही 0 है, फिर बाकी 4 आपस में कैंसिल हो जाएंगे.
0x and 0y and 0x 1y. Where are my 0x's? I still have to compute my, I haven't yet computed my these terms. Okay, 0x 1y, all of these are 0. Correct? बिल्कुल. Calculations are going to yield. So now if we were to complete our calculations, so now let's write down the dynamical matrix on its own. So what we're going to do now is we're going to write down these dx's. These dx's are the sum of all of these phi's. So this term over here in this big bracket with the 1 over m included is my dxx. And this term in my big bracket with the 1 over m is my dxy. So now I'm going to write down the matrix itself, minus omega square plus dxx. So I'm trying to write down the dynamical matrix plus minus omega square into identity. Minus omega square plus dxx is 1 over m, okay. Now my phi's, phi 0x is 2 alpha plus beta plus, now let's look at phi 0x 1x and phi 0x 3x. This is minus alpha. Minus alpha. Now the exponential factors, once I have kw1 in the exponent with an iota, and then I have minus I kw1. So this gives me 2 cosine of kw1. So I get 2 alpha cosine of kw1. Now kw1, w1 is along the x-axis and has a length a, right? So I will get the x component of k, which is kx, into a. Okay, beautiful. And then I take into account the other 4 terms, 0x, 5x, 0x, 7x. So this is from 0x and 3x. 0x and 2x and 0x and 4x give me nothing, they give me 0. Then 0x, 5x, 6x, 7x, 8x, all of them give me minus beta by 2. So I get minus beta by 2, and I get, now these 2 terms, kw5 and k minus w5, will give me 2 times cosine of kw5. Now w5 is all of this. So I get akx plus aky. So I will get 2 times cosine of kxa or akx plus aky. Okay. Now let's consider these 2 terms, 6 and 8. 6 and 8 are still minus beta by 2. 2 times cosine of, now omega 6 and omega 8, or w6 and w8, they are minus akx plus aky. So they will give me cosine of akx minus aky. So this, by the way, if I remove this minus omega square, this, by the way, is dxx plus, am I missing out something? No, that's fine. This is my dxx. And I can simplify this. I can take my 2 as common, 2 over m, alpha plus beta minus alpha cosine of kxa minus beta over 2 cosine of akx plus aky plus cosine of akx minus aky. Now I can use a trigonometric identity here. This will be cosine akx, cosine aky twice. So I'll get minus b cosine akx cosine of aky. Alpha plus beta minus alpha cosine of akx 2m. This is my dxx. Got it? Likewise, my dxy. My dxy is somewhere this, all of this 1 over m, these 1 over m, this phi x 0 y, this is 0. Now 5y and 7y, 5y and 7y are minus beta by 2, 2 times cosine of kw5. Once again, akx plus aky, and from 0 x6y, 0 x6y, and I get plus b by 2, 2 times cosine of akx minus aky. This yields minus beta over m cosine minus sine, minus 2 sine, I get plus 2 beta over m sine of akx sine of aky. This is my dxy. Okay? I employed a trigonometric identity. By the way, I need 4 elements in the dynamical matrix. I now need a second row. Now if this is dyx, what should be dxy? It should really be the same, because this in effect is the force on an atom along x when another atom moves along y. That will be the same as the force acts on an atom along y when the other atom moves along x. It's symmetric. And you can immediately see that this will be true if I were to replace this n and m, if I were to swap this n and m. It's a symmetric force. If I were to swap these and I swap these, the result would still be the same. Okay, so swapping A and B doesn't change this dynamical matrix element. In other words, the dynamical matrix element is symmetric. So this would be the same as dyx. I only need to compute dyy. Okay, that needs to be computed, because there will be additional terms of the kind phi 0 y ky. So when I do all of this, the final matrix that I get is the only change that can you guess what your dyy is going to look like? Just swap. Is there anything unique that is present in dxx? So this has both akx and aky. So this term is fine. But this term is uniquely akx. So dyy, so if I were to replace this with a y over here, so if these terms were to be y, dyy, just simply replace this kx with a ky. Okay, so now I have all my d's in really, really nice shape, and I have this matrix, in other words. So this matrix, in other words, I can compose everything together, and I'm left with, from equation number 2, I'm left with minus omega square plus dxx plus 2 over m alpha plus beta minus alpha, okay, I can write a alpha 1 minus cosine kxa plus beta 1 minus cosine kxa cosine kya. Two beta over m sine of kxa sine of kya, 2 beta over m sine of kxa sine of kya minus omega square plus 2 over m alpha 1 minus cosine of kya plus beta. I just want to make sure it's plus beta. Yes. 1 minus cosine kxa cosine of kya ux uy, this must equal 0. From here I can find the dispersion relationship. So if I take this matrix, find its determinant, equate it to 0, I will get a relationship of omega squared, the frequency squared, with k's. Okay. Now suppose I would like to plot these dispersion relationships. Just want to see if we still have time. So if I look at my reciprocal space, the picture in the reciprocal space, this is my origin of the reciprocal space. I have a kx direction and I have a ky direction. So this is my origin. I know that this is the first Brillouin zone, so this point here must be pi over a kx and ky is minus pi over a. That's this point here. Remember, this is the first Brillouin zone. This point is pi over a minus pi over a minus pi over a minus pi over a pi over a. So I've drawn the Wigner-Seitz cell in the reciprocal space, and this is just a square. This length, of course, is 2 pi over a on each side. It's a square reciprocal lattice. Now I want to find out how. Now the k is varying in this first Brillouin zone. In one-dimensional dispersion relationships, I plotted omega versus k. Now I need to make a three-dimensional plot of omega versus any point in this first Brillouin zone. Now I can keep things simple as well. So generally, what physicists do is that they plot dispersion relationships along fiducial directions. For example, this center of the reciprocal space is called the gamma point. And you can move from this gamma point to the edge of the first Brillouin zone, to the zone boundary. The zone boundary, let's call this point X. Now these are special symbols that are used, and we've already highlighted these symbols in one of our early classes. So as you move along this line gamma to X, your ky is 0. So along this line ky is 0. And you can find out the dispersion relationship on any point on this gamma X line. Any point which is generally given the symbol delta on this gamma X line. So what you could do is you could make a plot as you go from omega to X. This is your K variable, Kx or Ky. So as you go from omega to X, you can plot your omega. So along this line, what is varying is Kx. So here, you can keep in your mind that your Kx is varying and your Ky is 0. You can plot that whatever dispersion relationship you get. Let's see what that plot looks like. I'll show you in a minute. Now, by the way, how many branches would exist for this dispersion relationship? There are n atoms, and there is one atom per basis, so n times 1, but the number of dimensions is 2, so there are x and y motions are possible, so there are 2 branches that can exist, and both of them will be acoustic branches. So I'll show you on the computer what those branches look like. But then you could also move from X to some other point, say M. And you can make a plot as you go from X to M along this section of, along this special line of the Brillouin zone. Your Kx here is fixed at pi by A. Remember, this point is Kx equals pi by A. And your Ky is varying from 0 to pi by A. So you get this branch. And then you can also come back from M to gamma point. So you can come back from M to gamma and plot whatever relationship you get over here. Along this line, your Kx equals Ky. And here Kx and Ky are both pi by A, and here both of them are 0. So you move along this line, and you can find out the dispersion relationship at any intermediary point on this line, which is generally called a sigma point. So these are the special lines in the first Brillouin zone over which you can plot your dispersion relationships. Now I've plotted these dispersion relationships for your convenience so that you can understand what's going on. So let me kind of, in the last 2 or 3 minutes, what I've done over here is kind of looked at, use some specific values. So alpha I just take to be 1 unit and beta is half of it. And my unit length A lattice vector, I take this to be 1 unit. And then along the gamma x line, I find out omega 1 and omega 2, the 2 roots for the determinantal equation, which the determinant is set to 0. So in this equation over here, I put ky 0. So this ky becomes 0, this term becomes 1, this term becomes 0, 0, 1 minus cosine of kxa, and so on, right? Did I miss an alpha plus beta? Oh no, I haven't. So I put in along this line ky equals 0, and I solve this equation for omega, and I get 2 roots. Of course I get 2 roots because I have 2 branches, and these are what my roots look like. Okay, so these are acoustic branches. Both of them start at omega equals 0. Here their slope specifies the speed of sound inside the medium. Okay, So if the speed of sound is equal to the slope of this equation, which is omega over k, and that dispersion relationship extends all the way, it's dispersionless, then I can find the Debye frequency. But there is dispersion because the slope is changing. But both of them correspond to acoustic branches.
अभी हम इसको phase velocity कहेंगे, group velocity.
There is no concept of phase velocity here because there is dispersion. So the group velocity, which is the slope of this curve, is some finite value over here, and here the group velocity is 0, which means that there is a discontinuity in the density of states, which is called the Van Hove singularity. So there is a discontinuity in the density of states, because the density of states is inversely proportional to the slope of this curve. So these are the phonon branches, the acoustic phonon branches for the gamma x line. Now I move from x to m. So what I've done over here is I've found out these curves, okay? Now let's move from x to m. And when I do that, I get these lines. So this curve moves back a little bit, this curve moves up a little bit. And they converge at point M. Okay? So the two acoustic curves kind of converge. Here you will find another discontinuity in the density of states, because the group velocity again is 0. One of these curves is a longitudinal acoustic branch and the other is a transverse acoustic branch. Okay? Finally, if I move back from M to gamma, I can plot this section of the dispersion relationship. And this is what this looks like. Okay, so here sorry. And they meet again here over here. This point, of course, corresponds to this point. So they must be identical here. At each of these sections, you get an omega, and it starts off in the next section from the same point. Okay, so this is what the dispersion relationship looks like. Now you can experimentally determine these dispersion relationships as well. And that will be my last lecture on this topic next week. Okay, so this is how phonons exist inside 2 dimensions. In fact, I can plot this in 3D as well. I can plot this not just along these symmetrical lines, but also at any other point inside the first Brillouin zone. And this structure, this dispersion relationship, also obeys certain symmetry. First of all, is symmetric along K. It's a mirror image along K. The second point is that it has the same point group symmetry as the lattice itself. So for your convenience, I've actually plotted all 3 of these sections along these special symmetry lines all together from left to right in exactly the same way as I've drawn on the blackboard. This is the gamma x section, this is the xm section, this is the m gamma section. And I can also plot this in 3D. So for 3D, I take the entire matrix, which is I've defined as Q, with all kx, all ky's included. And I find its determinant, put it equal to 0, and solve for omega. I get 2 negative roots which are meaningless. Omega is always positive. and I pick up the positive roots and plot them in 3D, like a surface plot. So this is the kind of plot that I get for the two branches. So I can kind of tilt and turn around and see what it looks like in 3D, right? This is what it looks like. Okay, and it's immediately obvious at the gamma point, everything kind of boils down to 0. And this is obviously seen at this apex point. And this kind of floats around, this kind of expands a little bit and then comes down.
सर कि 2D में तो हमें इस सिनेरियो में नजर आ रहा था कि जो कैलम ब्लू वाला ग्राफ है वो ऑरेंज के नीचे जा रहा था, लेकिन 3D
नहीं इधर तो नहीं जा रहा, कहाँ जा रहा है?
सर जब हम यहाँ से वहाँ जाते हैं फ्लिप नहीं हो रहा है?
नहीं ये
मतलब एक ऊपर जा रहा है एक नीचे जा रहा है।
हाँ, ये इंटरसेक्ट नहीं कर रहे।
वही तो, एक ऊपर जा रहा है एक नीचे जा रहा है। अच्छा, इंटरसेक्ट नहीं कर रहे।
इंटरसेक्ट नहीं कर रहे हैं। These branches are not intersecting. Right, so this is, I've plotted one separately and I plotted the other one separately as well. The two branches are plotted here as well.
तो एक ऊपर ही रहता है।
एक ऊपर ही रहता है। हाँ, so how many modes exist? How many, so if you look at quantization here, it depends upon the number of atoms. So n atoms, 2 dimensions, each one of these branches will have n points on it. So there will be 2 n points inside the K space because there are 2 n degrees of freedom. All right. So there could be 2 n phonons inside the system at the most. Right, so that also determines the Debye frequency. So this is how we kind of plot dispersion relationships in 2D. You can extend this to 3 dimensions, but then it gets more and more complicated. So in homework number 5, I will give you some problems related to, say, a hexagonal matrix. So I would ask you to compute the phonons in graphene, which has a hexagonal 2-dimensional structure. So you will construct your D matrix. For that, you need to construct your phi's according to the same prescription that we have that we've seen today, and find out the dispersion relationships for graphene, phonons inside graphene. Okay, so now let's take a 5-minute break.